Hello listeners and viewers. Welcome to Kaduna State Ministry of Education Radio and TV e-learning program designed for our SS3 and other students staying at home due to the coronavirus pandemic. The present administration, under the able leadership of His Excellency, Malam Nasir Ahmed El-Rufai, is positioned as always to ensure that under his leadership, our students are not left behind in all areas of human endeavors, especially education. Kaduna State is the center of learning. Therefore, we want to ensure that our students excel in their forthcoming examinations and beyond. Students and other learners at home are given this opportunity in order to continue learning, as education is a continuous process. Different subjects will be taught in this program to assist students to perform excellently in the forthcoming Senior School Certificate examination being conducted by NECO and WAEC as soon as schools reopen. Teachers making presentations will always provide their names and phone numbers during each presentation, and they can be contacted for questions, further explanations, and/or clarifications. The following numbers and contacts can also be reached for expression of any concern or observation: 090-865-00545 or 080-383-62072. Our website is www.education.kdsg.gov.ng. Our email education@kdsg.gov.ng or education.kdsg@gmail.com. Our YouTube channel, Ministry of Education, Kaduna State. Our Twitter handle @Kaduna_MOE. Or our Facebook page, Ministry of Education, Kaduna State. Stay safe, stay at home, and learn well. Thank you, happy listening, and happy viewing.
Hi, learners. You are once again welcome to our e-learning program organized by Kaduna State Ministry of Education. And today we are discussing on the topic Heisenberg uncertainty principle under physics. We define Heisenberg uncertainty principle as follows. It states that it is practically impossible to measure or determine or locate an exact position of a particle and the momentum of such a particle at the same time or simultaneously. What this means is this: it's not possible that you measure a particle that is stationary and at the same time you measure the movement of that particle. That is, an object cannot be stationary, static, or at a point and at the same time moving. That is what this concept is all about. But then it is possible you can measure one of such quantity at a time, and then another time you measure the other quantity. And that is, it's possible to measure either position of a particle at one time, then you measure the momentum of the same particle another time. The precision in measuring one quantity is high, but then there is a greater uncertainty, deviation, aberration in the measurement of the uncertainty of the other quantity at the same time. And then we said we have this defined or mathematically expressed as follows. If we have delta x as an uncertainty in change in measurement of a given position of a particle, and of course this particle we are talking about is elementary particle, that is subatomic particle like electron, proton, and neutron. If delta x is an uncertainty, that is a change in the measurement of the position of such a particle, and delta p is an uncertainty in the measurement of the momentum of that same particle, then we see that the product, that is, if we multiply delta x by delta p, you will get that is either greater than a constant known as Planck's constant, or it is equal to it. And mathematically, it is expressed as delta x dot, or multiplied by delta p, greater or equal to h, giving us equation 1. You either make delta x, that is, the uncertainty in position of such a particle, the subject, giving us delta s greater or equal to h over delta p as equation 2, or you make delta p the uncertainty, the change in momentum of such a particle as a subject, and that will give us delta p greater or equal to h over delta x as equation 3. But now we know that momentum is a vector quantity, and it's a product of mass and the velocity of the body. And that will give us P equals to mv as equation 4. If equation 4 is substituted in equation 1, we will see that our equation 1 will naturally give us delta x dot m dot delta v greater or equal to h. Before then, the symbol delta or change, of course, acts only on vector quantity. But because momentum is a vector quantity, as I said, and the product of mass and velocity, mass is a scalar quantity. If you substitute that p into delta p equal to delta bracket mv, the delta acts on v and not on m, because v is a vector quantity, velocity of the particle. And so our equation 4, p equal to mv, gives you delta p equal to delta bracket mv as equation 5. And so we withdraw our m outside the bracket to give you equation 6, delta p equal to m delta v. If that is substituted in equation 1, then we will have delta x. Instead of delta p, we will have delta x dot m delta v, greater or equal to h, still our Planck constant. And so we divide both sides by m, the scalar quantity, and it will give us delta x dot delta v greater or equal to h over m as equation 8. As I said, we either make either of the physical quantity the subject. The uncertainty in momentum could be made a subject, or the uncertainty in position as above. And the same case is applicable to the one we have just arrived at. That is delta s dot delta v. We make delta x a subject to give us delta s greater or equal to h over m delta v. Delta s dot delta v greater or equal to h over m. Making delta s a subject, you have delta s greater or equal to h over m delta v, giving us equation 9. Otherwise, we make delta v the subject, and it gives us delta v greater or equal to h over m delta x as equation 10. This principle is not only applicable to position and momentum, or position and velocity. It's also applicable to a variable that is a pair known as energy and time. The uncertainty principle can also be applied to the measurement of the energy, capital E, of an object at a particular time, t. If the uncertainty in E is delta E and the uncertainty in T is delta T, then we will find that our delta T multiplied by delta T, so delta E multiplied by delta T, that is delta E dot delta T, will be greater or equal to. This time around, it's not Planck constant. It's Planck constant bar, that is h bar. And that will give us equation 11. This is different from the variables we have considered. And the h bar there implies h bar equals to h over 2 pi. That's the meaning. So if we substitute that into equation 11, it will now give us equation 12, which is delta E dot delta T greater or equal to h over 2 pi in place of h bar. And making again delta E the subject, it will give us delta E greater or equal to h over 2 pi delta T. As I say, we can also make delta T the subject, and if it happens, we will now have delta T greater or equal to h over 2 pi delta E, giving us equation 14. As I said, in one of the lessons that you don't get scared with the number of equations you have. There are basic foundational or elementary equations that you should bear in mind, which are the ones applicable to especially the variable you have. We have equation 1 is our basic formula, and equation 4. If you can remember equation 1, equation 4, and then equation 11, that is all about it. These 3 equations are enough. All we need to do for others is just to make some adjustment and you play around the equations. The 14 equations shouldn't scare you. So if you're asked to calculate any of the parameters, all you need to do is remember equation 1, equation 4, and equation 11, and no trouble. By the time you remember the equation after sorting the data, then you'll be able to apply. We go to our examples. So that's a concept about Heisenberg uncertainty principle. Example 1, find the uncertainty in the measurement of momentum of a particle. If the uncertainty in the measurement of its position is 5 times 10 to the power minus 10 meter, Planck constant is given as h equal to 6.6 times 10 to the power minus 34 joules second. For the solution, always sort out data. Write out whatever information given to you in the problem. Then the unknown which you are asked to find, you put a question mark against it. That would be a pointer as to which equation is suitable for application. In this solution, you have delta x, which is the uncertainty in position equal to 5 times 10 to the power minus 10 in meter. H, Planck's constant 6.6 times 10 to the power minus 34 joules second. And then delta P is what we are asked to find. And of course, you know that the suitable equation for use is equation 1. Delta x dot delta P greater or equal to H. And all you need to do is to make our equation delta P the subject, giving you delta P greater or equal to H over delta x. Substitution will give you delta P greater or equal to 6.6 times 10 to the power minus 34 over 5 times 10 to the power minus 10. When computation takes place, you will have delta P greater or equal to 1.32 times 10 to the power minus 34 times 10 to the power 10. In mathematics, the elementary topic indices implies that these two indices, minus 34 and power 10, all in power will be added. And if it happens, then you are going to have your final result will be delta P greater or equal to 1.32 times 10 to the power minus 24 Newton second. It's Newton second because momentum is a product of change, is a change of velocity, or is a product of force and time, which is equivalent to impulse. And that's the unit you have there, Newton second. Otherwise, it can be kilogram meter per second as an alternative unit for it. Example 2. In example 2 also, we have this given, the uncertainty in the velocity v of a moving electron of mass 10 to the power minus 34 kilogram is 3 times 10 to the power 6 meter per second. We have to calculate the uncertainty of the simultaneous measurement of the position of that particle. Planck constant again is given, and then the value of the mass of that particle is 10 to the power minus 30. That is a solution given to us there. M equals to 10 to the power minus 30 kg, and the velocity is v is equal to 3 times 10 to the power 6 meter per second. The Planck constant, as I said, is also given 6.6 times 6.62 times 10 to the power minus 34 joules second. What we are asked to find there is the uncertainty in position. Again, our number 1 formula, you just apply E delta S dot delta P greater or equal to H, making our substituting P into the by substituting P by mv, you will have delta S dot delta bracket mv greater or equal to H. Delta S dot M delta V greater or equal to H, making that delta S a subject. Delta S give you greater or equal to H over M delta V. This is when you can just apply the first formula and recollect the fourth formula, as I said. Otherwise, you can go and make your quotation of what you have there in the formulas you have derived so far. And substitution will now give us greater or equal to, for the Planck constant, 6.62 times 10 to the power minus 34 as the value, and then the mass is 10 to the power minus 30, while the velocity uncertainty is 3 times 10 to the power 6. Again, if you compute, you will have the value of the uncertainty in position greater or equal to 2.21 times 10 to the power minus 34 times 10 to the power 24. And then you will have delta x greater or equal to 2.21 times 10 to the power minus 10 meter. Now, in physics, there is a given unit that can replace 10 to the power minus 10 meter, and we call it Armstrong unit. So in place of E, we just use this letter A to power naught. And that will give us in place of this. This is important because options may be given to you not in meter, it may be given to you in Armstrong unit, whichever examination body you are approaching. Otherwise, we also have alternative way of expressing the unit we have here. Apart from meter and Armstrong unit, you can also express it in submultiple of units. And that is delta S greater or equal to 0.221 times 10 to the power minus 9. That is, if you express this as 10 to the power minus 9 from equation from this place, you will see that this 10 to the power minus 9 is the same as nanometer. So in place of this in meter, we have 10 to the power minus 9 is nano. The small n there stands for nano, and so that is nanometer. So you have 0.221 nanometer. If that is given to you in option, please don't get confused. Just know how to compute it. We also have alternative unit which can be expressed. This value you have can also be expressed in picometer, and that is exactly what you have. And different other ways of making the expression of your unit in submultiple. And example 3 goes thus. The uncertainty in position X of an electron through a cathode ray tube is 1 Armstrong unit. What is the uncertainty in the velocity? Assuming the mass of that particle is 10 to the power minus 30 kilogram. H equal to, as usual, delta S, uncertainty in position is 1 Armstrong unit, as I said, is 10 to the power minus 10 meter, the whole of it. So our mass is in 10 to the power minus 30 kilogram, Planck constant given, and then we are asked to find the uncertainty in velocity. Again, our delta X dot delta P greater or equal to H is the same as delta S dot delta bracket MV, all close and then greater or equal to H. And then delta S dot M delta V greater or equal to H, delta V greater or equal to H over M delta X. Substitution gives you 6.6 times 10 to the power minus 34, and the mass is 10 to the power minus 30. The uncertainty in position is 10 to the power minus 10, and then you compute to give you delta V greater or equal to 6.6 times 10 to the power minus 34 times 10 to the power 40. And by the time you do it, you have delta V greater or equal to 6.6 times 10 to the power 6 meter per second. And as I said, apart from some multiple of units like your picometer, nanometer, we also have multiple units. The 10 to the power 6 is represented by capital M, and it means mega. So we can say, instead of saying delta V greater or equal to 6.6 times 10 to the power 6 meter per second, we can say delta V greater or equal to 6.6 mega meter per second. Example 4. A proton of an approximate mass of 10 to the power minus 24 kg has an uncertainty position of 1 picometer, and that's explained in bracket as 10 to the power minus 12 meter. Moving with a non-relativistic velocity of 10 to the power 8 meter per second, we have to calculate the percentage uncertainty in momentum. Planck constant is given. The solution is as thus: m equals to 10 to the power minus 27 kg. Delta S is your picometer, which is the same as 10 to the power minus 12, and then the velocity, non-relativistic, is 10 to the power 8 meter per second. Uncertainty in momentum percentage is percentage delta P, which is a question mark. That's why we have to find. How do we find that? The formula is given as percentage uncertainty or momentum is delta P over P. That's uncertainty and momentum over momentum times 100%. We are to find percentage, we are to find delta P, uncertainty and momentum, and to find momentum itself. Planck constant is given. Then from the formula delta S dot delta P greater or equal to H, we substitute the value A delta P greater or equal to H over delta X greater or equal to 6.63 times 10 to the power minus 34 over 1 times 10 to the power minus 12. And then delta S gives us 6.63 times 10 to the power minus 34 times 10 to the power 12. Delta P greater or equal to 6.6 times 10 to the power minus 22 Newton second. But then we will calculate momentum to give us P is equal to mv, and the mass is given as 10 to the power minus 27, and the velocity is 10 times 10 to power times 10 to power 8, and it gives us 10 to power minus 19 Newton second. The percentage, therefore, of uncertainty in momentum will give us percentage delta P equals to, substitution give us from the formula given 6.63 times 10 to power minus 22 over 10 to power minus 19, all multiplied by 100%. When it happened, the percentage in uncertainty of momentum will be 6.63 times 10 to power minus 22 times 10 to power 2 times 10 to power 19%. And by the time the 10 to power 2 implies our 100, and then by the time you have that delta P, the percentage in delta P will give you 6.63 times 10 to power minus 3 percent. And in a normal decimal fraction, percentage in uncertainty and momentum will be 0.663%. Question 5, our last problem example. The uncertainty in determining a duration during which an electron remains in a particular energy level before returning to the ground state is 2 nanoseconds. And then calculate the uncertainty in determining its energy at that level. Again, we said this is different from the pair variables of delta x, delta p, delta x, delta v. Delta E and delta T are related by h bar. That is, your Planck constant bar, and h bar has been given as h over 2 pi. When you substitute, you have pi is a normal pi. The circumference of a circle divided by the diameter, which is 22 over 7, is a constant. The 2 remain, and the Planck constant, we have 1.054 times 10 to the power minus 34 joule seconds. Solution will now be delta T is equal to 2 nanoseconds, which is 2 times 10 to the power minus 9 seconds. Delta E is what we are asked to find. Delta E dot delta T greater or equal to h bar. Delta E dot delta T greater or equal to h bar over 2 pi. And delta E greater than or equal to h over 2 pi delta T greater or equal to 1.054 times 10 to the power minus 34 times 1 over 2 times 10 to the power minus 9. That's by substitution. And then you have delta E greater or equal to 0.527 times 10 to the power minus 34 times 10 to the power 9. And then you have delta E greater or equal to 5.27 times 10 to the power minus 26 joules. Please, our energy can be expressed in not only joules, electron volts. And if you do, you divide by the electronic charge 1.6 times 10 to the power minus 19. It gives you 3.29 times 10 to the power minus 7 electron volt. We further express it in submultiple to be delta E greater or equal to 0.329 times 10 to the power minus 6, which is the same as a micro. Thank you for listening. Listen, take over to my colleague as he comes to summarize the lesson.
Good day, learners. My name is Hassan Buki. I will just summarize on what my colleague, Mr. Napoleon Kure, has already delivered to you. Heisenberg uncertainty principle. What Heisenberg is telling us in his principle is that it is practically impossible to measure precisely the position and momentum of a particle at the same time, that it is not practically possible to do that. And the uncertainty in the measurement of position is delta x, and the uncertainty in the measurement of momentum is delta p. And we saw that their product is greater or equal to Planck's constant, which is small letter h. And we went ahead to see that this principle could also be applied in the measurement of energy of an object. That is what Heisenberg is telling us in his principle. And he gave you so many equations, and he has given you so many examples to see how these equations could be applied. Now, I am going to give you assignment that you will practice at home, and after you have finished, you can send it to us through our contacts, which I will later give you. Assignment. Question number 1 says, what is the uncertainty in the measurement of time if the uncertainty in measurement of energy of an electron of mass 10 raised to the power of minus 30 kilogram is 2.45 times 10 raised to the power minus 19 joules. Given that Planck's constant small h is equals to 6.63 times 10 raised to the power of minus 34 joules second. Then we have Planck's constant bar to be equals to Planck constant all over 2 pi, which is small h all over 2 pi. Question number 2. Calculate the uncertainty in the position of a particle of mass 10 raised to the power of minus 8 kilogram, moving with a velocity of 10 to the power 4 meters per second, given that Planck's constant, small h, is equal to 6.63 times 10 raised to the power minus 34 joules second. Question 3. The uncertainty in the energy of a particle is 1.0 times 10 raised to the power minus 10 joules. Determine its uncertainty in the time measurement, given that Planck's constant, small h, is equal to 6.62 times 10 raised to the power minus 34 joules second, and Planck's constant bar is equal to Planck's constant h, small h, divided by 2 pi. I take the questions again. Question number 1. What is the uncertainty in the measurement of time if the uncertainty in measurement of energy of an electron of mass 10 to the power of minus 30 kilogram is 2.45 times 10 raised to the power minus 19 joules, given that Planck's constant, small h, is equal to 6.63 times 10 raised to the power minus 34 joules second, and Planck's constant bar is equal to Planck's constant, small letter h, divided by 2 pi. Question 2. Calculate the uncertainty in the position of a particle of mass 10 raised to the power of minus 8 kilogram, moving with a velocity of 10 to the power 4 meters per second, given that Planck's constant, small h, is equal to 6.63 times 10 raised to the power minus 34 joules second. Question 3. The uncertainty in the energy of a particle is 1.0 times 10 raised to the power minus 10 joules. Determine its uncertainty in the time measurement, given that Planck's constant, small h, is equal to 6.62 times 10 raised to the power minus 34 joules second, and Planck's constant bar is equal to Planck's constant divided by 2 pi. So please solve these questions and get back to us on these contacts. We have Mr. Napoleon Kure on 08036362105 and Hassan Buki on 08065504346. I take it again. Napoleon Kure 0803636 again 2105. Hassan Buki 08065504346. You can get back to us either through WhatsApp or SMS. Thank you till we meet again in the next lesson.